Good day and welcome to my YouTube channel. I'm Arthur Francis Deba. We say the Boyle's law, the volume of a given mass of gas is inversely proportional to its what? Pressure if the temperature is constant. So we're going to look at it from the mathematical point. If we say that the volume of a given mass of gas is inversely proportional, which is 1 over, to its pressure if the temperature remains constant. So from here, we have our volume, we remove this proportional sign to equality sign, and we bring a mathematical constant K, alright, which is over P. So our constant is equal to Vp. Therefore, we say V1, P1 is equal to what? V2, P2. Where V1 is the initial volume, initial pressure, final volume and final pressure, which means the system, when heat is being applied or whatever, the volume will increase and the pressure will equally increase, so we have our V2P2. From here, we can proceed on to do whatever calculation we want. And graphically, we can also say that the volume, if we have a direct proportional sign here, the volume will be inversely to the pressure. And so on, there are many other symbolic diagrammatical representation which we can deal with. And about the direct inversely proportional stuff, we also have something like this. Remember, okay, when the volume increases, when the volume is small, the pressure will be big. As the volume increases, the pressure will be reducing. So when we say inversely proportional, that simply means that when the volume increases, pressure will decrease. When the pressure increases, the volume will decrease. That's inversely proportional. So the kinetic explanation of all of this. Remember I told us earlier that the collision of the gas molecules, the kinetic energy there, therefore, gives rise to its pressure. Therefore, if the volume of the gas in the cylinder is reduced by half, then the collision of the gas molecules will increase double of the sign of the time, because the distance from where it is to the walls of the cylinder is twice. So therefore, the collision increases, as such, the pressure will increase. So when we reduce the volume by half, the pressure will increase double. So when we increase the volume, we fill the cylinder, the pressure will reduce by half. So that is how that goes. So in the kinetic explanation, that is how it is being revealed. So let us take some questions to see how we can go about this whole thing. All right, our first question. A certain mass, I'm going to read it, I don't have to write it out. Then I bring out the given values and we solve. A certain mass of gas occupies 200 cm cube at 1.0 times 10 raised to the power 5 Newton per meter squared. Calculate its volume when the pressure is 2.0 times 10 raised to the power 5. So we have our initial volume, which is our V1. When the pressure increase, or the pressure increased by 2, the volume will tend to increase by 2, which means we'll go down to the final volume. So at constant temperature. So let's take our given. While I read, first of all, it is important we have what we call given. We have V1, P1, V2, P2. Okay, I say a certain mass of gas occupies 200 cm cube, which is our V1. 200 cm cube. At 1.0 times 10 raised to the power 5, which is our P1. 1.0 times 10 raised to the power 5 Newton per meter squared. We should calculate its volume, V2. So we don't know what that is. That's what they say we should calculate. When the pressure increases to 2.0, 2.0 times 10 raised to the power 5 Newton meter. Okay, that is it. Remember, according to Boyle's law, they say the volume of a given mass of gas is inversely proportional to its pressure. Where we say volume is equals to K over P, making K the subject, we have Vp. Where we say that V1 P1 is equals to V2 P2. You don't forget that. That is what we're going to use to solve. So, if that is true, let me just put it here so we can always reflect. Now, V1 P1 is equals to V2 P2. We are looking for V2. So V2 is equals to V1 P1 all over P2. And this is equals to the volume V1 is 200 cm times the pressure is 1.0 times 10 raised to the power 5 Newton per meter square all over the P2, which is 2.0 times 10 raised to the power 5 Newton per meter square. So, when we use our calculator, we see what we get. So we have our 200 times 1.0 times 10 raised to the power 5 divided by 2, also divide by 10 raised to the power of 5. So that is 100. So our V2 is 100 cm3. So that is it about the first question. So let's take our second. We say a given mass of gas at 55 degrees Celsius, which is temperature, has a pressure of 3.6 times 10 raised to the power 4 Newton meter or Newton per meter square, and occupies a volume of 1.8 dm cube, which is our first volume, yes. What volume will it occupy, the V2? They are asking if its pressure is increased to 4.8. So from P1, we have gone to P2. So remember, temperature is constant. We say that the volume of a given mass of gas is inversely proportional to its pressure. What at constant temperature? If the temperature is constant, you get that. Or if it is not constant, then the law will not be obeyed. So let us bring out our given. So in question 2, given, we have our V1, P1, V2, P2. Now, a given mass of gas at 55 degrees Celsius has a pressure of 3.6 P1, 3.6 times 10 raised to the power 4 Newton per meter square, and occupies a volume of 1.8 dm cube. V1 is 1.8 dm cube. Okay. What volume will it occupy, the V2? What volume will it occupy if its pressure is increased to 4.8? 4.8 times 10 raised to the power 4 Newton per meter square. We still simply just apply the law, the formula. What does it say? We say our V1 P1 is equals to V2 P2. So if we are looking for V2, we'll make it the subject of formula, which is V1 P1 all over P2. And this is equals to our V1 here is 1.8 dm cube times P1 is 3.6 times 10 raised to the power 4 Newton per meter square over P2, which is 4.8 times 10 raised to the power of 4 Newton per meter square. So this is equals to So we check again with our calculator. 1.8 times 3.6 times 10 raised to the power of 4 divided by 4.8 times 10 raised to the power of 4 is 1.35. So 1.35 gm cube is our final volume. So we take another question. Our third question here, if 375 cm cube of a gas has a pressure of 770 millimeter mercury. So we have our V1 and our P1. Find its volume, the V2, if the pressure is reduced to 750 millimeter mercury. Okay, that is our P2. Okay, I have my V1, P1, V2, P2. V1 says 375 cm cube. Okay, of the gas has a pressure of 770 millimeter of mercury, which is another value or unit for pressure. Find its volume, V2. We should look for that. If the pressure is reduced to 750 millimeter of mercury. So we proceed. Our formula again says V1 P1 is equals to V2 P2. We are looking for V2 again. I guess we're going to see question where we have to look for some other thing. So our V2 is equals to V1 P1 over P2. And this is V1 here is 375 cm cube times P1 is 770 millimeter of mercury over P2, which is 750 millimeter of mercury. So let's go. We have 375 times 770 divided by 750. 385. So our V2 is equal to 385 cm cubed. So we move on. We have more questions here. Okay, we're just done with this. Our fourth question says 200 cm cube of a gas has a pressure of 510 millimeter of mercury. What will be its volume if the pressure is increased to 780 millimeter of mercury, assuming there is no change in temperature? Remember, we say in Boyle's law that the temperature is always constant. So assuming that there is no change in temperature, which means the temperature remains what? Constant. So let's go with that. Now, okay, 200 cm cube, which is V1, 200 cm cube of a gas has a pressure of 510 millimeter of mercury. What will be its volume, V2, if the pressure is increased to 780 millimeter of mercury? That's our fourth question. We go again. V1 P1, V2 P2. V2 is equals to V1 P1 over P2, which is equals to V1 is 200 cm cube times P1 510 millimeter of mercury over P2, 780 millimeter of mercury. And V2 is equals to, we have 200 times 510 divided by 780. That is 130.8. 130.8 cm cubed, which is 131 cm cubed. Three significant figures, very important. Our fifth question. Okay. What pressure will be required to compress 350 cm cube of hydrogen at 700 millimeter mercury to 300? So let's get a question. Say, what pressure will be required to compress? We already have 350 cm cube, which is our V1 of hydrogen, at 700 millimeter of mercury, which is our P1, to 300. So that is now our V2, all right? Temperature remaining constant. So we are going to be looking for P2 now. So let's take this out. What pressure will be required to compress 350 cm cube V1, 350 cm cube of hydrogen at 700 millimeter of mercury, 700 millimeter of mercury, to 300 cm cube what is the pressure? So this time we're looking for P. Here again we have our V1 P1 is equal to V2 P2. We are looking for P2, so we have P2 is equal to V1 P1 over V2. So that's change of subject of formula in math. Someday we're going to have it treated in math. Okay, I have this already, so let's do. V1 is 350 cm cube times P1 is 700 millimeter of mercury. Yeah, boys. Over V2, which is 300. So I have 350 times 700 divided by 300. 817. P2 was 817 millimeter of mercury. Okay. Let's take our sixth question. A gas has a volume of 500 cm cube when a pressure of 76 millimeter of mercury is exerted on it. What will its volume be if the pressure on it is changed to 73 millimeter of mercury, assuming temperature remain constant? So we're looking for V2 this time around. So let's take this out. Okay, let's say a gas has a volume of 500 cm cube. 500 cm cube when a pressure of 76 millimeter of mercury, 76 millimeter of mercury is exerted on it. What would its volume be, V2, if the pressure on it is changed to 73 millimeter of mercury? V1, P1, V2, P2. We're looking for V2. V2 is equals to V1, P1 over P2. And this is V1 is 500 cm cube times P1 is 76 millimeter of mercury over P2, which is 73 millimeter of mercury. So I have 500 times 76 divided by 73. 521. V2 is equal to 521 cm cubed. Yeah, it's in cm cubed. So this is our final volume. Okay, let's just take 7 questions and move to something else. The 7th question, we can stop there. Let me clean it up. A gas occupies 200 cm cube. 200 cm cube at 510 millimeter of mercury. 510 millimeter of mercury. If temperature remains constant, what will its pressure be when the volume is increased to 131? 131 cm cube. What will its pressure be? So we have this now. Back to our formula, V1 P1 is equals to V2 P2. We're looking for P2 now. So P2 is equals to V1 P1 over V2. That is equals to V1 is 200 times P1 is 510 over V2 is 131. And this is equals to, so check, 200 times 510 divided by 131 is 779. 779 millimeter of mercury. Okay, then we can stop it there. Let's go to another law, the Charles law. Let me take this out. Now, in Charles' law, we say the volume of a given mass of gas is directly proportional to its temperature in Kelvin if the pressure remains constant. In the Boyle's law, the temperature was constant, but in the Charles' law, the pressure is constant. So, in that case, let's look at it mathematically, then we see what we have. So we say that the volume of a given mass of gas is directly proportional to its temperature in Kelvin, which means V is equals to KT. This is the mathematical constant. If I make my constant the subject, I will have K is equals to V over T. So this is what we have. Now, how do I explain this? They say that the volume is directly proportional. Kinetically, according to the kinetic law or explanation, it means that when the volume of a given mass of gas increases at constant pressure, the temperature will increase, and vice versa. So this is the mathematical explanation, which means that V1 T1 is equals to V2 T2. So this is how this law goes, and so on and so forth. So let us see by solving one or two questions. Diagrammatically, it means the same thing, that the volume is directly proportional to temperature. Directly. So as this one increases, this increases, and that tends to continue. So in all ramifications, when your volume increases, your temperature increases. So let's take some calculations. So we have V over T. Take note, we don't forget this. So question number 1 says, the volume of a fixed mass of gas measured at atmospheric pressure. Okay, measured at atmospheric pressure and 27 degrees Celsius is 3.0 dm3. We should calculate the volume at blah blah blah. Let us find out our values. The given is always this way. Sorry, let me shift this a little bit down this way. So V1, T1, V2, T2. Remember, V over T. So we go. Let's take the question now. The volume of the fixed mass of gas measured at atmospheric pressure and 27 degrees Celsius is 3.0 dm cubed. So V1 is 3.0 dm cubed. 3.0 dm cubed. And the temperature therein, let's say, is 27 degrees. T1 is 27 degrees Celsius. Okay. Calculate the volume, V2, at 127 degrees Celsius. 127 degrees Celsius. And at the same pressure. So the pressure is constant. Remember, I talked about the real value for temperature, that the temperature, the official value is in Kelvin. Okay, unless if you're asked to leave your answer in degrees centigrade, then you can leave it there. But if you are not asked, you have to take it to Kelvin, because we say the volume of a given mass of gas is directly proportional to its temperature in Kelvin. Okay, provided the pressure remain constant. So we have to convert this to our Kelvin scale. And we say, for us to convert it to our Kelvin scale, we have to add 273, okay, which is the standard value for temperature. So now, we want to do that. So let's say, if I take this as a plus 273, put my K, I'm just trying to follow the rules here, plus 273, put my K. So this will give me, I have 27 plus 273, that gives me 300. So 300 Kelvin. 127 plus 273 is 400. So I have 400 Kelvin. Now, the law or the formula says V1 T1 is equal to V2 T2. We are looking for V2. So my V2 is equal to V1 T2 over T1. And this is equal to, in case we don't understand, we cross multiply. This times this is equal to this times this. So we have V1 T2. We divide both sides by T1. That is what is left. So my V1 is 3.0 dm cubed times T2 is 400 Kelvin over T1 is 300 Kelvin. This is equals to, so I have 3 times 400 divided by 300. It's 4. So I have 4 dm cubed as my final volume. So that's our first question. Let us move on. Question number 2. A given mass of gas occupies 500 cm cube. 500 cm cube. At 25 degrees Celsius, T1, 25 degrees Celsius, so let's say plus 273. Okay, calculate the temperature in degrees Celsius at which its volume doubled at constant pressure. So the volume doubled. If it was 500, it will become 1000. So they say we should calculate the temperature in degrees Celsius. Remember I said the official value is in Kelvin, So when we are done having our answer in Kelvin, we minus 273. We take it back to the Celsius scale. So from here, the formula says V1 T1 is equals to V2 T2. But then we're looking for T2, so T2 is equals to T1 V2 over V1. And this is my T1, which is 25 plus 273 is 298. So this is 298 Kelvin. So I have T1 is 298 Kelvin times V2 is 1000 cm cubed over V1 is 500 cm cubed. So if I have my 298 times 1000 divided by 500 is 596. So T2 is 596 Kelvin. If I minus 273, I will be left with, because I have to take it back to the Celsius scale, minus 273. 323 degrees Celsius. So that is my answer, because I was instructed to leave it in the centigrade scale. Okay, let's proceed to the third question. It says a gas sample with initial volume 3.25 dm cube, 3.25 dm cube, is heated and allowed to expand to 9.75 dm cube, 9.75 dm cube at constant pressure. What is the ratio of the final absolute temperature to the initial absolute temperature? So this is important. So we're looking for the ratio of the initial and final temperature. So this is all that is given to us. So remember, before we get into the business, let me give us a scenario of comparison. If I have A over B is equals to C over D, according to ratio, it means that A is equals to C, A is over C, this, and this is equals to B over D. So this over this equals to this over this. In ratio is the same thing. So if this is true, let us compare with what we have. We have V1 T1 is equals to V2 T2. If this is true, that also means that V1 over V2 is equals to T1 over T2. And this is, V1 is 3.25 dm cube. Is to ratio of V2 is 9.75 dm cube. Remember, that is equals to this over this. So according to ratio, we divide by the smallest. So this is over 3.25 dm cube. 3.25 dm cube. So this is obviously 1:, we'll come back here, we have 9.75 divided by 3.25. This is 3, approximately 3. It therefore means that 1/3 is equals to T1 over T2. So the ratio is 1:3. So that is what they are asking of us. So that's all. Let us move on. Question what? 4. Okay. A fixed mass of gas of volume 546 cm3. 546 cm3. At 0 degrees Celsius. 0 degrees Celsius plus 273 is equals to 273 Kelvin. Is heated at constant pressure. What is the volume of the gas at 2 degrees Celsius? 2 degrees Celsius plus 273 is equals to 275 Kelvin. Sorry. No, that's not it. It said, what is the volume? So we're looking for V2. That's not supposed to be there. What is the volume? The air is 2 degrees Celsius. So we just add our 273, which is 275 Kelvin. Okay. That's true. Let's proceed. We have our formula. V1 over T1 is equals to V2 over T2. So we're looking for V2. So V2 is equals to V1 T2 over T1. And this is equals to V1 is 546 cm3 times T2 is 275. Yeah, 275 Kelvin. This is over T1, which is 273. 273 Kelvin. And this is equals to 546 times 275 divided by 273. 550. So this gives us 550 cm3 as our final volume. Let's take our 5th question. Our 5th question says, a fixed mass of gas occupies 40 cm3 at 0 degrees Celsius. So we have our V1 and T1. Let's take out this. A fixed mass of gas occupies 40 cm3. This is 40 cm3. At 0 degrees Celsius, T1, 0 plus 273, that gives us 273 in Kelvin. Find the temperature at which its volume becomes 54.7. Volume becomes 54.7 cm3. Assuming that its pressure remains constant. So we're looking for T2. We go again. V1 T1 is equals to V2 T2. We're looking for T2 here. So our T2 is equals to T1 V2 over V1. And this is equals to T1 is 273 Kelvin times V2 is 54.7 cm3 over V1 is 40 cm3. And this is equals to, our T2 will be 273 times 54.7 divided by 40. 373 Kelvin. Okay, we'll take, that's the 5th. Let's stop at 7, the 7th question, probably. 6 now. The sixth question says, a certain mass of gas occupies 300 cm cube at 35 degrees Celsius. 300 cm cube at 35 degrees Celsius. So we'll add 273. We take it to Kelvin. Okay. At what temperature will it have its volume reduced by half? At what temperature will the volume of this reduce by half? So if you reduce by half, that becomes 150 cm cube. Now the formula says V1 T1 is equals to V2 T2. We're looking for T2 now. So T2 is equals to T1 V2 over V1. V1. And this is equals to, what is T1? Oh, sorry, let me add that. 35 plus 273. 273 is equals to 308. So this is 308 Kelvin. So my T1 is 308 Kelvin times V2 is 150 cm cube over V1 is 300 cm cube. And this T2 becomes 308 times 150 divided by 300. 154 Kelvin. So that is our sixth. Oh, is that our seventh question? Okay. 300 at 35. At what temperature will it have its volume reduced? Okay, that's our sixth question, I guess. Let's take the last question on this. A sample of gas has a volume of 500 cm cube at 45 degrees Celsius. What volume would the gas occupy at 0 degrees Celsius when the pressure is constant? A sample of gas has a volume of 500. V1 is 500 cm cube. At 45 degrees Celsius, T1 is 45 degrees Celsius. So I just want to take this out and add my 273, and that will give me something in Kelvin. What volume would the gas occupy, V2, at 0 degrees Celsius? 0 plus 273 Kelvin. When the pressure is constant, pressure is always constant. Okay, I have my 45 plus 273, 318 Kelvin. So V1 T1 is equal to V2 T2. I'm looking for V2. So V2 is equal to V1 T2 over T1. And this is my V1 is 500 cm cube times my T2 is 273 in Kelvin over T1 is 318 in Kelvin. And that final volume is 500 times 273 divided by 318, 429 cm cube. Okay, that is that about the Charles law. Now, the general gas law encompasses the Boyle's law and Charles law together. So let's see what we have in the general gas law. So let's see how we combine them. First of all, we say Charles' law says the volume of a given mass of gas is directly proportional to its temperature in Kelvin. The pressure is constant. Boyle's law says the volume of a given mass of gas is inversely proportional to its pressure if the temperature is constant. This volume is directly proportional to this, volume is directly proportional to this. It therefore means that we can have it as volume which is directly proportional to temperature times 1 over P, which is this. And if that is true, volume now equals to, we bring our K, T, times 1 is the same, over P. If I make my K the subject, I cross multiply, this is over 1, I have KT is equals to VP. Now, divide both sides by T, so K is equals to Vp over T. This becomes our general gas law. So now we have volume V1 for initial, P1 for initial, T1 for initial is equals to V2 for final, P2 for final, T2 for final. So I can easily write that here. That's too hard. Let me see. So I can just have it here as Vp over T to remember. A certain mass of gas occupies 330 cm3. So our constant, our given, will always be this way. V1, P1, T1, V2, P2, and T2. Okay, let's see. A certain mass of gas occupies 330 cm3. 330 cm3. At 27 degrees Celsius. That is T1. 27 plus 273. Whatever we get there. And 9.0. Sorry, that's temperature, not pressure. 27 comes down here. 27 plus 273. Okay, at 9.0. 9.0 times 10 raised to the power of 4 Newton per meter squared. Calculate its volume at STP. Now, when we are calculating the volume at STP, at standard temperature and pressure, we say the standard temperature is 273. The standard pressure is, in Newton meter, is 1.0 times 10 raised to the power of 5. So we just have to put that down. But the question says, calculate its volume, so we are looking for V2. Standard pressure is 1.0 times 10 raised to the power of 5 Newton per meter squared. Standard temperature is 273 Kelvin. So this is also, what do you get? 27 plus 273 is 300. 300 cm3. Now, the formula. We have V1, P1, T1 is equal to V2, P2, T2. We are looking for V2. So my V2 here will be V1, P1, T2 over T1, P2. If that is true, my V2 is equals to, my V1 here is 330. I don't want to put the unit because of the space, times P1 is 9.0 times 10 raised to the power 4 times T2, 273 over T1 is 300 times P2, where are you? which is 1.0 times 10 raised to the power of 5. Then V2 is equals to this. Okay, we start with 330 times 9 times 10 raised to the power of 4 times 273. We divide by 300 equals to, we now divide by 10 raised to the power of 5. This is 270.3 perhaps. So let's take 3 significant figures as 270. So this is 270 cm cubed. So that's our first question. The second question, I'm not going to take much. Let me take out this and leave the given. The second question, what volume will 200 cm cube of hydrogen measure at 25 degrees Celsius with pressure of 600 Newton meter occupy at STP? So let's start. What volume will 200 cm cube, V1 is 200 cm cube, of hydrogen measured at 25 degrees Celsius, temperature is 25 plus 273. Where is it? With pressure of 60,000, sorry. Yes, 60,000. Okay, that is my P1. Good. At standard temperature and pressure, they say what volume? So we're looking for V2. V2, we don't know. P2 is always a standard temperature pressure 1.0 times 10 raised to the power 5 Newton per meter square. Standard okay, yeah, right. So temperature is in Kelvin, 273 Kelvin. Let's add that to get that of our T1. 25 plus 273. 273 is 298. Here is 298 Kelvin. Okay, let's go again. V1, P1, T1 is equal to V2, P2, T2. We are looking for V2. So V2 is equal to V1, P1, T2 over T1, P2. If that's true, V2 would therefore be V1 is 200 times P1, which is 60,000, 60,000. T2 is 273 over T1, 298 times P2 is 1.0 times 10 raised to the power of 5. So my V2 would be, so now I have 200 times 60,000, 1, 2, 3, times 273, 3, divided by 298, 298, divided by 10 raised to the power of 5. 109.9. 109.9 cm cubed. This is our final volume. So, the volume of a given mass of gas is 300 cm cubed at 27 degrees. Okay, and 700 millimeters. So, let's start. The volume of a given mass of gas is 300. V1 is 300 cm cubed. At 27 degrees, 27 plus 273, and 700 millimeters, 700 millimeter of mercury. What would be its volume? V2 again. If it's okay, what would be its volume at 36 degrees Celsius? T2, 36 degrees Celsius and 750 millimeter of mercury. 750 millimeter of mercury. So here we have again 36 plus 273. 273 is equals to 309. 309 Kelvin. Where again, yeah, T1. 27 plus 273, 73. It's 300. 300 Kelvin. We go back to our formula. We have our V1, P1 over T1 is equals to V2, P2 over T2. We are looking for V2 again. Whoa. So V2 is equals to V1, P1, T2 over T1, P2. So V2 is equals to, V1 is 300, P1 is 700, T2 is 309, T1 is 300, okay, times P2, P2 is 750. 750. So my V2 would be so my V2 will be 300 times 700 times 309 divided by 300 divided by 750. That's 288.4. So we can just say 288 cm³ as our final volume. The fourth question. What is the volume at STP of a fixed mass of gas that occupies 700 cm³? That is our V1 at 25 degrees Celsius. That is our T1, and 0.84 as our P1. So let's start. What is the volume at STP of a fixed mass of gas that occupies 700 cm³? As our V1, 700 cm³. At 25 degrees Celsius, T1, 25 plus 273. And 0.84 times 10 raised to the power 5 times 10 raised to the power 5 Newton per meter square. What is the volume at standard temperature and pressure? I think that's all we need. So now, what is our P2? Our P2 here is 1.0 times 10 raised to the power of 5 Newton per meter square. Our T2 is 273 Kelvin. So if that is true, our V2 is equals to V1 P1 T2 over T1 P2. V2 is equals to, my V1 is 700 times my P1 is 0.84 times 10 raised to the power 5 times my T2 is 273 over my T1 is 25 plus 273 which is 298. Yeah, it's 298 Kelvin. So T1 is 298 times P2, 1.0 times 10 raised to the power 5. Okay. Quickly, I have 700 times 0.84 times 10 raised to the power of 5 times 273 divided by 298 divided by 10 raised to the power of 539 cm3. Last question for the day. Let's take, at STP, a certain mass of gas occupies a volume of 800. Okay, our V1 is 800. Find the temperature at which the gas occupies 940 cm cube. Okay, 940, that's our what they call it, V2, 940, and has a pressure of 675, that is P2. Okay, let me clean this. So I have my P1 is 760. A mass of gas occupies a volume of, okay, my V1 is 800, V1 is 800. It's 800, my T1 is 273 Kelvin. Okay. My P2, where is it? Okay. P2 is 675, P2. 675 millimeter of mercury. Okay, and my T2 is lacking, that's what we're asked to get. What is left? My V2, what volume is that? 940 cm3. Okay, we are looking for T2 now. So this is my T2. So T2, I change the subject to give me T1 V2 P2 over V1 P1. My T2 is equals to, my T2 is equals to, T1 is 273, 73 times, my V2 is 940 times, my P2 is 675, my V1 is 800, and my P1 is 760. And finally, I have my 273 times 940 times 675 divided by 800 divided by 760, 285. This is 285 Kelvin. So, in the general gas law, which we just finished solving, which was a combination of the Boyle's law and Charles' law, and the Boyle's law earlier, and the Charles' law, which we dealt with, which has to do with the volume directly proportional to its temperature, and the Boyle's law, the volume inversely proportional to its pressure. We have other laws that are found in this general gas laws, these gas equations and all that. We have the Avogadro law. We have many of them. So in our next class, we will tend to complete them all. So for today, thank you and have a nice day.